Welcome all. My name is Suresh and I am a lecturer in ECE from Government Polytechnic Belapalli. I am going to teach the subject electronic device and circuits, which is a common subject for both instrumentation and ECE students. Subject code is 18EI 303C. Today's topic is state the effect of negative feedback on gain. In the previous lessons, we have learned about the feedback, different types of feedbacks, derivation of the feedback gain, that is the closed loop gain, right? And we have seen the circuit diagrams of different types of feedback amplifier, that is voltage series, voltage shunt, current series and current shunt. Now we have to state the effect of negative feedback on gain. The gain with the negative feedback from the derived version of the previous lessons, we have AF feedback gain with feedback is equal to A by 1 plus A beta, where A is the open loop gain, or gain of the basic amplifier, and beta is the feedback ratio. For effective feedback, A beta is very much greater than 1. Hence, 1 can be neglected as compared to A beta in the above expressions. Effective feedback, we have A beta is very much greater than 1. Generally, the gain of amplifier at a stage, it is around 50 to 100, and the beta value which is more than 1. So obviously, A beta will be very much greater than 1. So we can neglect 1. So the overall equation will become AF is equal to A by A beta, which in terms still equal to 1 by beta. So AF literally equals to 1 by beta. So observe this equation. Gain with feedback, AF is equal to 1 by feedback ratio. So gain with feedback does not depend on the original gain. It is independent of the term A. So therefore the overall gain depends only on the feedback fraction beta. That is only the feedback circuit characteristics. The feedback circuit usually consists of resistive elements. Already we know that it is the resistive elements. The resistive elements are unaffected by variations in temperature, frequency and transistor parameters. Hence, the feedback fraction beta remains stable. As we know, the feedback network is a resistive network which consists of only some sort of resistors. So the resistors does not depend on the variation of temperature, frequency and transistor parameters. So the beta remains stable. Hence the gain of negative feedback amplifier is very stable. Next, state the effect of negative feedback and bandwidth. As we know from the definition of bandwidth, the bandwidth of an amplifier without feedback is given by BW is equal to F2 minus F1, where F2 and F1 are the cutoff frequencies. F2 is upper cutoff frequency, F1 is the lower cutoff frequency. So when we apply the negative feedback, the overall bandwidth, the negative feedback decreases the lower cutoff frequency. The lower cutoff frequency of an amplifier with feedback is given by F1 dash is equal to F1 by 1 plus A beta. The negative feedback increases the upper cutoff frequency, that is to value F2 dash. F2 dash is equal to F2 into 1 plus A beta. So F2 dash increases compared to F2 and F1 dash decreases compared to F1. So the overall bandwidth will become, that means the bandwidth after feedback, negative feedback is applied, the bandwidth feedback is given by bandwidth is equal to F2 dash minus F1 dash. Therefore the bandwidth is increased. Overall the bandwidth is increased. From the figure also we can see, in the figure the top curve, that is without feedback, and the lower curve, that is with feedback. You can see the change in the upper cutoff frequencies and lower cutoff frequency, and you can see the increase in the bandwidth from the diagram. So when we apply the negative feedback to a amplifier, the overall bandwidth will increase, right? The gain bandwidth product, GBW, gain bandwidth product, which is a very important parameter to select any amplifier, is the figure of merit of an amplifier, right? For an amplifier system, the gain bandwidth product is constant. When negative feedback is applied, the amplifier gain is reduced to AF, right? Gain is reduced, but the bandwidth increases. So the gain bandwidth product will remain same. Lower cutoff frequency is also known as lower 3 dB frequency or lower half power frequency, and the upper cutoff frequency is also known as upper 3 dB frequency or upper half power frequency. Next, state the effect of negative feedback on input impedance. What happens to the input impedance when we apply negative feedback to a without feedback amplifier? The effect of negative feedback on input resistance depends on the type of mixing, right? If you can remember the block diagram or the diagrams of the voltage series or voltage shunt, current series or current shunt amplifiers, there you can see the sampling and mixing networks, how they are connected either in shunt or in series, and what happens when they are connected in series or shunt to the resistances, that is input impedances or output impedances. So first, for the input impedance, when there is series mixing, it increases the input resistance by a factor of 1 plus A beta. In the series mixing, the resistors are added, right? So the resultant impedance will increase, and the input resistance increases by a factor of 1 plus A beta. Shunt mixing decreases the input impedance by the same factor. Same factor means here same 1 plus A beta factor. So shunt mixing decreases the input impedance and series mixing increases the input impedance. Next, effect of negative feedback on output impedance. Here the effect of negative feedback on output impedance depends on the type of sampling. The sampling network which is connected at the output takes a sample from the output given to the input to the network. The sampling, it can be either voltage or current, that is either shunt or series. So depending on that sampling, the resultant output impedance of the amplifier network changes. For current sampling, the output resistance actually it is okay. For current sampling, the output resistance increases by a factor of 1 plus A beta, because for current sampling you need to connect it in series, and for the voltage sampling it decreases the input impedance, so decreases the output impedance by the same factor, that is 1 plus A beta. Please correct here for the output impedance, this is output resistance, these two. The second point, current sampling increases the output resistance by a factor of 1 plus A beta, and voltage sampling decreases the output resistance or output impedance by the factor 1 plus A beta. Now moving on to the next topic, Effect of negative feedback on distortion and noise. These are also important terms to be considered when we select a amplifier for a particular operation or application, because though the gain and stability are good, but if the distortion and noise are not good, then the selection of amplifier will be in question, right? So what happens to the distortion and noise when we connect the negative feedback? Reduction in distortion. So with the negative feedback, the distortion will be reduced. It can be proved mathematically that df, distortion with feedback, is equal to d by 1 plus a beta, where d is the distortion without feedback and 1 plus a beta is the factor, general factor. You can remember from the previous slides. The gain af is equal to a by 1 plus a beta. Bandwidth dash is equal to bandwidth into 1 plus a beta, and the remaining terms, input impedance, output impedance, whether increases or decreases by the same factor, that is 1 plus a beta. So here also, in the case of distortion also, distortion reduces, but how much? It reduces by a factor of 1 plus a beta. So when the input signals are of large amplitude, distortion occurs due to non-linear characteristics of active device. Here in the transistor amplifier, active device is transistor. So with the non-linear characteristics of this transistor, when we apply the signals of large amplitude, there is a distortion possible. Distortion will occur. Reduction in noise. It can be improved mathematically that, so we have seen the reduction in distortion, that is df is equal to d by 1 plus a beta, and same the noise is also decreased by the same factor, that is nf is equal to n by 1 plus a beta. That is noise with feedback is equal to noise without feedback by 1 plus a beta. So the noise also reduced by a factor of 1 plus a beta. So note, unwanted signals in a circuit constitute noise. So what do you mean by noise? They are unwanted, though they are useful, but in that particular circuit, if we don't want to get that particular signal, then that can be considered as a noise. An amplifier without feedback without feedback amplifies noise and the signal to some extent, but negative feedback reduces noise by a factor of 1 plus a beta. So like that, distortion and noise reduces by the factor of 1 plus a beta. Now the advantages of negative feedback amplifiers. So why we need to select negative feedback compared to positive feedback? Advantages of negative feedback in an amplifier are given below. They increases stability, increased bandwidth, less amplitude and harmonic distortion, decreased noise, less frequency distortion, less phase distortion. Input and output resistances can be modified as desired. As desired means, if we can select the beta value, that means we can modify the beta value depending on the resistive network we use to constitute the feedback network. So beta is in our hands, so we can change the input and output resistance as we desire. Now comparison of different feedback amplifiers. So we have 4 different types of feedback amplifiers, that is voltage series, voltage shunt, current series and current shunt. So go for the comparison, different parameters. First, gain stability. Voltage series improves stability of voltage gain. Voltage shunt improves stability of RM, right? Resistive amplifier. Improves stability of GM, conductive amplifier. Current shunt improves stability of AI. Pure current amplifier. The bandwidth in all the cases, voltage series, voltage shunt, current series and current shunt, all the feedback amplifiers increases the bandwidth. Input resistance, as if we can remember from the previous lessons, input resistance depends on the mixing network, whether it is in shunt or series. If it is in shunt, it will be decreased. If it is in series, it will be increased. And the names voltage series, voltage shunt, current series and current shunts are first term voltage or current related to the sampling, and the second term series or shunt related to the mixing. So here for the input resistance to consider, we need to go for the second term. That is, if there is series in the second term, it will be increases. If there is shunt, it will be decrease. So see that voltage series increases, input resistance increases. Voltage shunt, input resistance decreases. Current series, input resistance increases. Current shunt, input resistance decreases. Now see the fourth parameter which is to be compared, that is output resistance. Output resistance, as we know from the previous slides, previous topics, we can remember that output resistance of feedback amplifiers depends on the sampling network, whether they sample the voltage or current. Depending on that parameter, they can be connected as either shunt or series. If they are connected in shunt, the resultant impedance will decrease. If it is connected in series, the resultant impedance will increase. So here the feedback amplifiers, voltage series or voltage shunt, the names, the first term is related to the sampling. So if it is voltage, the first term, if it is voltage, that is in shunt connection, the output resistance decreases. If it is current, it is in series connection, the output resistance increases. See that fourth output resistance, first one is voltage, here decreases. Second one is voltage, here decreases. Current increases, and again current, it will increase. Now the distortion, non-linear distortion, as we can remember from the previous slides, that is df is equal to d by 1 plus a beta, that is distortion decreases by a factor of 1 plus a beta in the negative feedback, right? Without considering either it is voltage series, voltage shunt, or current series or current shunt, the distortion will decrease. Now moving on to the topic next, noise parameter, it is also decreases. So with these 6 parameters, we compare the different feedback amplifiers. Now we need to solve simple problems on this effect of negative feedback on gain, bandwidth, input impedance and output impedance. Simple formulas, please note down those formulas, 4 formulas. On gain, AF is equal to A by 1 plus A beta, and you should know what is A, what is beta, right? And bandwidth dash is equal to bandwidth into 1 plus A beta, Z input, either depending on series mixing or shunt mixing, it is Zi by or Zi into. Next, Z output, it is also depends on the sampling. So depending on sampling, it will become Z0 into or Z0 by. So take down a pen and paper, please write the question. First question, calculate the gain of a negative feedback amplifier with an internal gain A is equal to 200 and feedback factor beta is equal to 1 by 20. Write down the question, calculate the gain of a negative feedback amplifier with an internal gain A is equal to and feedback factor beta is equal to 1 by 20. Just apply the formula, substitute the values and get the answer. Please do it yourself. It may take just half minute or even 1 minute itself, not more than that. The lecture can wait. Please do. Right? Does everybody completed? Just see the question once again. Whoever not completed or whoever completed, please check yourself whether you have done it correct or not. First, write the question again. Calculate the gain of a negative feedback amplifier. Right? It is a feedback amplifier and it is negative. With an internal gain A is equal to 200 and feedback factor beta is equal to 1 by 20. So what is the formula for the gain with feedback? That is AF is equal to A by 1 plus or minus A beta. Plus or minus is for, that means if it is negative feedback we will get plus, if it is positive feedback we will get minus. So the question here is negative feedback amplifier, so we will get AF is equal to A by 1 plus A beta, and we have given the two values, that is A. Internal gain A is equal to 200. Sometimes they don't give it as A, just directly give it as with an internal gain 200. So you should know what is the each literal meaning in that particular formula. And feedback factor beta is equal to 1 by 20. Just substitute them. What happens? AF is equal to A by 1 plus A beta is equal to 200 by 1 plus 200 into 1 by 20. 20 and 200 cancels 10. 10 plus 1 11. 200 by 11. So here is a mistake in the solution. Please correct it. 200 by 1 plus 200 into 1 by 20. 20 tens are the 20s are 200 by 11. We will get it as how much? Some 19.5 or something. Is it? Right. So those are the values, but observe the results. That means without feedback we have 200 is the gain, but with the feedback we have it around 19.5 something, right? So it drastically reduced, right? So the formula we means to get the AF value. Next question, please write down. The overall gain of a multi-stage amplifier is 100. When negative feedback is applied, the gain reduces to 10. When negative feedback is applied, the gain reduces to 10. Find the fraction of the output that is feedback to the input. Please write down the question and do it yourself. I can wait for 2 minutes. Please remember the formula because they have asked about only the gain with negative feedback. So AF is equal to A by 1 plus A beta. We have given overall gain, that means with feedback overall gain of multi-stage amplifier, total gain is 100, A is equal to 100, and with the negative feedback is applied, the gain reduces to 10. So sometimes the English words may confuse you. The gain reduces to 10, that is the gain became 10, not the gain reduces by 10. If she has given the word by, then you should calculate first the how much the gain became, and after that you should submit it. So here directly he has given AF is equal to 10 and A is equal to 100. So what is the term that we don't know in that formula with these substituted values? That is beta, that is feedback fraction. It itself asked in the question, that is the find the fraction of the output that is fed back to the input. He didn't directly ask the feedback factor, but asked the definition of the feedback, the definition of beta, feedback fraction, output of fraction of output that is fed back to the input. So these different types of question terms you should practice, but because in the exam they may not or may not directly give the values by mentioning beta, this is beta, this is A. So see the answer solution. You know that AF is equal to 1 A by 1 plus A beta, AF is equal to 10 and A is equal to 100. 10 is equal to 100 by 1 plus 100 into B, and with that we can get beta is equal to 0.09. So feedback fraction is 0.09, that is 0.09 fraction of the output is fed back to the input. So we have already known that sampling means collecting a simple sample value 0.09%. So 0.09, it is, if it in percentage we get, it is 9%. So we have stated up to 10%, right? So here we collected the 9%. So these are the practical values to make you understand and have an idea how much the values will be, practical values will be. Now next level of question, a negative feedback amplifier with A and beta and Vs, some values is given. Calculate the factors, that is gain with feedback AF, output voltage V output, feedback factor beta, and feedback voltage. So this is next level. Please read the question again. As a negative feedback amplifier, A, that is without feedback gain 100, beta fraction feedback factor, and Vs source voltage. Calculate these values. Please do it yourself. I can wait for 2 minutes. So all of you completed. I hope all of you has completed the answers. Now see the solution. First read the question properly again. Negative feedback amplifier with A value, beta value and Vs. Gain with feedback. As you know from the last two questions, AF is equal to A by 1 plus A beta. Output voltage, V output is equal to, actually AF is equal to what? V output by V source. So V output is equal to Vs into AF. Feedback factor, beta is the feedback fraction, not the factor. If you want the factor, we need A beta. Feedback voltage, Vf, beta is equal to what? Vf by V output. So Vf is equal to beta into V output. So you can calculate mathematically, right? 100 by 1 plus 0.04 into 100, V output, feedback vector and feedback voltage. Now moving on to the next question. With a negative feedback, an amplifier gives an output of 10 volts. With a negative feedback, amplifier gives output, V output, with an input of 0.5. When the feedback is removed, it requires 0.25 volts input for the same output. Calculate gain without feedback and feedback fraction, that is beta. You can see gain without feedback, A is equal to output by input. Output on 10, without feedback we need to give input as 0.25. So A is equal to 40, and gain with feedback, AF is equal to output 10 by input 0.5, it is 20. And the beta, if you want the beta, then AF is equal to A by 1 plus A beta. Substitute the values, you will get beta as 1 by 40. So these are the simple problems used to calculate the gain, bandwidth, input impedance and output impedance. Of course we have seen only about the gain and feedback factor, beta problems only. We can go for the next question, bandwidth, input impedance and output impedance also, because input impedance depending on the mixing, series Zi into the factor 1 plus A beta. For shunt, Zi is equal to Zi by 1 plus A beta. For output, Z output depending on the sampling. If it is voltage sampling, it is connected in shunt. So Z output is equal to Z output by 1 plus A beta. If it is current sampling, it is connected in series. Z output is equal to Z output into 1 plus A beta. So simple problems will be there. You can do them on your own. So today's topics, if you see that the effect of negative feedback on gain, bandwidth and input impedance and output impedance, distortion and noise, and advantages and comparison of these different feedback amplifiers. Now simple problems. Next, moving on to the third chapter of this subject, electronic devices and circuits, right? Chapter name is tuned and power amplifiers. In that The first one is subtopic. Explain the working of power amplifiers and tuned amplifier. That is the chapter name. First, state the need for a power amplifier. Till now, we have seen about the voltage amplification and current amplification. Now we have to see for the power amplifier. First, why we need a power amplifier? A transistor amplifier which raises the power level of the signal in audio frequency range is known as transistor power amplifier. An amplifier in which the power level of the signal rises that is known as transistor power amplifier. That is first definition. If you see the second one, it is defined as which converts DC power to AC power and whose action is controlled by the input signal. Actually, this is the accurate definition because the DC power which is supplied to the amplifier through bias voltages is actually converts into the AC power. That's why we get power increase compared to the input signal power. A power amplifier is an amplifier which is capable of providing a large amount of power to the load, such as loudspeaker or motor. In the real world applications, practical applications, the amplifier, the input is a small signal which has to be raised to a certain level so that the load can be driven. Load resistor can be driven. The practical loads are here we mentioned already. These are best two examples: loudspeaker and small DC motor or a motor. Power amplifier is also called the large signal amplifier. It is essential in almost all electronic systems where a large amount of power is required to be supplied to the load. Where there is a need, there should be an invention, right? When there is a requirement of large power, then we need to use large power amplifier. The power amplifier is used as the last stage in an electronic system. This one is important. When we use it in last stage, it will drive the load directly. A power amplifier is more commonly known as audio amplifier. The audio amplifiers are used in public addressing systems, tape recorders, stereo systems, television receivers, radio receivers, broadcast transmitters, etc. For example, a public addressing system consists of a microphone, multi-stage amplifier, and a power amplifier, and in the final output, that is a loudspeaker. All of us have seen this type of system, right? Public addressing system consists of a microphone, that is input, where we speak to that microphone. Multi-stage amplifier to amplify the signal, to change the frequency and tone of the signal. Power amplifier to boost the drive the load, that is typical loudspeaker. So the microphone converts the sound waves into electrical signal, which is a very low voltage, usually a few millivolts. Whenever we speak, our output, that is our acoustic waves, sound waves, are of low energy. They will be converted into low energy electrical signals, which is to be given to the input of multi-stage amplifier, which has to boost the signal power level of this weak signal, and it should drive to the end of the amplifier, where the power level is required to drive the output loudspeaker. The signal is insufficient to drive the loudspeaker, therefore this signal is first raised to a sufficiently high value, that is few volts, by passing it through a multi-stage small signal amplifier. Small signal means here voltage amplifier. The signal is then used to drive the power amplifier because it is incapable of delivering a large amount of power to the loudspeaker. There we need a power amplifier. In a public addressing system, to convert the sound signal, that is from mechanical vibrations to electrical signal, we need microphone. But the level of voltage is very low, so it should be amplified using a multi-stage amplifier, in which in that multi-stage amplifier first stages are typically low signal amplifiers, that is voltage amplification is done. But at the end amplifier has to drive the large loads, which consists of high power level, so it has to be the large signal amplifier, that is a power amplifier, in order to meet the requirements. So this is the introduction about the power amplifier, and regarding other topics we can learn from the next lesson. So today's topics are this. If you have any doubts, please mail me at sureshakul2001@gmail.com, and for the lab experiment, go to the VLabs virtual labs, and for the standard books, go to the Google and search electronic device and circuits by Millman and Hackins or Jacob, and other local authors are also available, and practice the questions. Study well, prepare well. Thank you one and all. Closing the session.